Let us look at binomial series. Now let's go back a little bit to high school maths. Remember, a plus b to the power of 0 is 1. A plus b to the power of 1 is a plus b. A plus b square is a square plus 2ab plus b square, and so on. Here, let's focus on the coefficients here in the expansions. If the exponent is n, expression is this, coefficients are listed below in a particular manner called the Pascal's triangle, and these coefficients are also written in the form of combinations. Let's very briefly figure out how this combination form helps us in figuring out the coefficients. So we know NCR, that is choosing R objects from N objects, is given by n factorial by n minus r factorial times r factorial. So let's look at a few examples. Let's say 4C2. What does this mean? N is 4, R is 2. That means we are choosing 2 objects out of 4 objects. That is given by 4 factorial by 4 minus 2 factorial times 2 factorial, and simplifying it we get 6. Now let's see whether it is actually 6 or not. So the power is 4. So n is 4, and the third term, because we are starting from 0. So 0, 1, 2, 0, 1, 2. So 6 is the coefficient. Similarly, 4C3 gives us the coefficient of a plus b to the power of 4. And in that, we get the 0, 1, 2, 3. That is 4. Similarly, 3C2 gives us 3, which is actually 3. Now, this is pretty straightforward. But suppose we want to know the coefficient of a plus b to the power of 10. And we want the 8th term's coefficient. Then we can't be expected to keep building this triangle. So that is where this combination helps. So 10C7, simplifying it, we get 120. So this was just a brief introduction kind of thing. Now let's proceed to binomial expansion for n in natural numbers when the exponent is a natural number. Now let's take 1 plus x to the power of n. If we expand it, we get this nc0 times 1 to the power of n times x to the power of 0 plus nc1 times 1 to the power of n minus 1 times x to the power of 1, and so on. So here what is happening is that c in the subscript, it is increasing 0, 1, 2, 3, 4, and so on up to n. The power of 1 is reducing. So n, n minus 1, n minus 2, n minus 3, and so on up to n minus n. And the power of x is increasing from 0. So 0, 1, 2, 3, and so on. Now we can evaluate this, all these combinations. Here nc0 is 1. 1 to the power of, actually it should be 0. So 1 to the power of 0 is 1. X to the power of 0 is 1. So everything is 1. So we have 1 as the first term. Plus nc1 is n. 1 to the power of 1 minus 1 is 1. X. So we have nx. And similarly for the rest of the terms. So here the r plus 1th term of the expansion is n times n minus 1 times n minus 2 dot 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 n minus r plus 1 divided by r factorial times x to the power of r. for all r in 0, 1 to n. R plus 1th term can also be written in this form of the combination form. So r plus 1 term is equal to combination nr times x to the power of n. And if you look at this expression, you will note that it is a finite series, or simply we can say it is a polynomial. Now, what if it is integers, specifically negative integers? So let n equal to minus m, where m is in the natural numbers. Then the binomial expansion of 1 plus x to the power of n becomes an infinite series and is valid for magnitude of x less than 1. So, for example, we have n equal to minus 1, let's say. Then 1 plus x to the power of minus 1 is equal to 1 by 1 plus x. Now, how do we resolve this into an expansion? By using our old friend, that is long division. So we are dividing 1 by 1 plus x. And if you go through this, you will notice that the power of x keeps increasing. That means it is going to be an infinite series. And the signs keep alternating. Plus, minus, and so on. So we have 1 by 1 plus x is equal to this expansion. Now, this is an infinite geometric series with alternating signs. So which means we can write it using the sigma notation. 1 plus x to the power of minus 1 is equal to the summation as n goes from 0 to infinity of minus 1 to the power of n times x to the power of n, where the absolute value of x is less than 1. Now let's look at another example where n is equal to minus 2. Now, unlike the previous example where n was equal to minus 1, we don't have to use long division for this. So let's see how this works out. From example 1, we had 1 plus x to the power of minus 1 equal to 1 minus x plus x square minus x cube dot dot dot. So 1 plus x to the power of minus 2 is equal to 1 plus x to the power of minus 1 times 1 plus x to the power of minus 1. So we can use this itself to evaluate for minus 2. So we have 1 plus x to the power of minus 2 is equal to this times this. Now here, constant term will be 1. 1 times 1. If you multiply any of the other terms, you will not get 1. Now, coefficient of x is minus 1 plus minus 1, which is equal to minus 2. Now, how did we get this? 1 times minus x and minus x times 1. Only by multiplying these specific numbers, we are going to get a term with x. So minus 1 plus minus 1 equal to minus 2, which will be the coefficient of x. Similarly, coefficient of x square is 1 plus 1 plus 1, which is equal to 3. So from, how do you get this? 1 plus 1, 1, 1. How do we get x square? 1 times x square, right? Then we have minus x times minus x. And we have x square times 1. And similarly for coefficient of x cube gives us minus 4. So 1 plus x to the power of minus 2 is equal to 1 minus 2x plus 3x square minus 4x cube and so on. So this again is going to be an infinite series. And we can write this as 1 plus x to the power of minus 2 is equal to the summation as n goes from 0 to infinity of minus 1 to the power of n times k plus 1 times x to the power of n, where absolute value of x is less than 1. So in general, we have 1 plus x to the power of minus m is equal to summation k equal to 0 to infinity of minus 1 to the power of k combination m plus k minus 1k times x to the power of k, with absolute value of x being less than 1. Remember, this is nothing but m plus k minus 1 c k. So for n in natural numbers, the binomial expansion is a finite polynomial. Whereas for n in negative integers, the binomial expansion is an infinite series valid for absolute value of x less than 1. Now let's look at binomial expansion for n in q backslash z. What does that mean? Means rational number excluding integers. So in the following cases, assume that p is in an integer and q is a positive integer, q is greater than 1, and GCD of p and q is equal to 1. Why all these conditions? Let's see. Q is in positive integers to make sure that we don't end up with a 0 in the denominator. Q greater than 1 to avoid an integer of the form p by 1. Because integer cases we have already seen. And GCD of p comma q equal to 1 to avoid p by q simplifying to an integer. So that's why these conditions are there. And absolute value of x is less than 1 to ensure convergence with additional consideration required at the endpoints for absolute value of x equal to 1. Now let's look at the different cases. So first case, 1 plus x to the power of p by q. Expanding it, we get 1 plus p by q times x by 1 factorial plus p by q times p by q minus 1 by 2 factorial times x square, and so on. Simplifying it by combining these terms, we get p minus q by q, p minus q by q, p minus 2q by q, and so on. Simplifying it further, all these q's we bring it down. So we have 1 plus px by q times 1 factorial, p times p minus q times x square by q square times 2 factorial, and so on. So now in series notation, we will have 1 plus x to the power of p by q is equal to summation n equal to 0 to infinity of p times p minus q times p minus 2q and so on up to p minus n minus 1q by q to the power of n times n factorial times x to the power of n. Just to confirm this, for n equal to 0, the first term has no factors in the numerator and hence taken as 1. And we know q to the power of 0 is equal to 1. 0 factorial is equal to 1. So which means everything is 1. That means the first term is 1, which is what we have. So that is the expansion of 1 plus x to the power of p by q. Now this can be written as summation n equal to 0 to infinity of p by q choose n times x to the power of n, where absolute value of x is less than 1. Now let's look at the next case. The first one was 1 plus x to the power of p by q. Now we have 1 minus x to the power of p by q. Expanding it, same procedure. We end up with this expression. And this can be written in summation notation, series form. So summation n equal to 0 to infinity of p times p minus q, p minus 2q times and so on up to p minus n minus 1q divided by q to the power of n times n factorial. Times, now here's the critical thing. Because of this minus, we have alternating signs. So we have minus 1 to the power of n times x to the power of n. And here the series converges when absolute value of x is less than 1. It also converges in the previous case also, 1 plus x to the power of p by q. Now let's look at the third case. 1 plus x to the power of p by q was the first one. Now we have minus p by q. So what happens in this case? We end up with 1 minus p by q times 1 factorial x plus p times p plus q by q square times 2 factorial and so on. And here again you will notice that the signs are alternating. So we have 1 plus x to the power of minus p by q, this expression with the extra factor, that is minus 1 to the power of n. And again the series converges when absolute value of x is less than 1. Let's look at the fourth case. 1 minus x to the power of minus p by q. This was 1 minus x to the power of p by q. So here again, if we expand it, you will notice that there are no alternating signs. It can be written in this form. Or we can use combination form also, and it will become much shorter. And the series converges when absolute value of x is less than 1. So we have seen 1 plus x to the power of p by q, 1 minus x to the power of p by q, 1 plus x to the power of minus p by q, and 1 minus x to the power of minus p by q. In case of rational exponents, plus p by q or minus p by q, the numerator of the nth term consists of factors which are in arithmetic progression with a common difference of plus or minus q, starting from plus p or minus p. Let's look at nth term. So p times p plus q times p plus 2q. So you will notice p plus q, p plus 2q, p plus n minus 1q. All these are in arithmetic progression. Or we can say the factors of the nth term in the numerator are in arithmetic progression. In this arithmetic progression, we are starting with what? We are starting with p. And we have a common difference of plus or minus q depending on the case. Now, as we saw, when p by q is in natural numbers, basically including 0 here, the expansion is a finite series or a polynomial. P by q is a negative integer. The expansion is a converging infinite series if absolute value of x is less than 1. And p by q, rational number excluding integers. The expansion is a converging infinite series if absolute value of x is less than 1. Let's look at this case. We have 1 plus x to the power of p by q. Here, the factors in the nth term, they will keep reducing, or we say falling, and there are no extra factors. That is minus 1 to the power of n. Nothing like that. 1 minus x to the power of p by q, again falling factors. But here in this case, we have minus 1 to the power of n as an extra factor because of the alternating signs. 1 plus x to the power of minus p by q. Now here we will have a rising factors with alternating signs. So which means we have an extra factor minus 1 to the power of n. And finally 1 minus x to the power of minus p by q. Again we have a rising factors in the numerator with no extra factor. This is very, very important. In the next session, we will look at some worked examples to figure out what concretely is happening. Because here we have looked at it in abstract. So that was binomial series. Now, if you found this session helpful, please do like, share, and subscribe. Comment suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.